Okay, resuming the recording, hopefully. So I'll just go to the directory we were in. Okay, so there's a file rational.sage that I just created, and I should be able to do sage-t rational.sage. And what this does is it will load all the code that's in the file and then run the tests. And it ran one test, and the test passed. Of course, you might not believe that because, I mean, it would be much more impressive if the tests were wrong and it said, ooh, it's failed. So let's do that. Let's just change the test in the file, rational.sage, so that it fails. So how about if I just put 389 here, my favorite number. Go back to the command line, run the test, and we hope very much to get a big error message here. Yes, there's an error. It says one of the tests failed, expected that, but it actually got that. Okay, so you can see how this can be really useful when you're developing code. Right, you put your code in a file, you put tests in, and then you can add new things. And if you break any of your tests, you'll find out very quickly that you did so. And that is will save you an enormous amount of time. And this sort of care where you write lots of tests that verify numerically what's happening works. There's two things. When you're writing mathematics code, it's really, really important to do this because the slightest mistake can just completely throw everything off. But at the same time, it's kind of really hard to, so like if you're writing a game or something, you just play it for a few minutes and you can kind of see whether you completely broke it or not. But with, okay, maybe that's not quite true, but depends on the game. But with some things you can do that. With math code, it's kind of hard to even create the objects that you want to work with. And also you have to think, oh, like if you slightly change some number, you have to remember sort of. So you really just want to do it this way because it really nails down what you're doing. Okay, so let's fix this one test because that was kind of disturbing. Oops, that's not the right fix. And then make sure it really works. Okay, so that is how you can put code in a file and test it. All right, so we now have a rational number and it normalizes nicely. So what should we do next with our rational number? It's really not very useful yet. Anybody want to do, what would you do, what sort of operations might you do with a rational number? Add. Okay, let's implement addition. So does anybody remember the name of the dunder method for adding two things, which we used for hours last time? Add. Yep, simple as that. Okay, so we're going to add a new method to our class called add. So I'll just put it right here. The order in which you put the methods doesn't matter at all, technically, as far as Python is concerned. It's purely up to you and your artistic inclinations. Okay, so we're going to add self and right. Self, maybe, I mean, it's normally called self, but maybe, yeah, I'll just call it self. So you're adding your rational number to anything. This method will get called in most cases if you write rational number plus anything at all. We're going to just, for simplicity, assume that the other thing is a rational number. That's not at all guaranteed, but we'll just assume that. You might do something like if not is instance right rational number. So okay, type rational number. Raise type error. So what that little bit of code does is it ensures that right is an instance of this rational number class or of some class that derives from it. We haven't talked about classes that inherit from base classes, but we will. So that's what this code does. It's purely a runtime thing. Python has no type checking like you would have in Java or other languages where, or at least Python 2 does it, where you explicitly declare the types of each of the inputs and are guaranteed that they have those types. There is some type annotation stuff in Python, but it doesn't actually guarantee anything at runtime without additional work. And I don't think it's in Python 2 anyways. So what this line does is it says if this thing isn't true, boom, make an error message appear, or basically raise an exception, which could get caught at some higher level using try except. And the exception is a type error, which means there's something wrong with the type of the input. And then this thing is instance. This is a built-in function in Python. It takes, on the left hand, just some Python object, and on the right you can get a class or a tuple of classes. And it is true exactly if the thing on the left is of the type on the right or of any of the types of the tuple on the right or something derived from them. So if you look in, say, Sage, or definitely in Sage, but in many Python libraries, you'll see tens of thousands of is instances. They're all over the place. It's an extremely common thing to see. By the way, there is a command which you can use from the terminal. If you say sage space dash grep, what this will do is it will search through all of the Sage source code for the word that you put, the word or phrase that you put on the right. So I'm using Unix stuff here that most of you don't know about, but what this means is run grep on the entire Sage source code, searching for all instances of the string is instance, and then take the results and pipe it into word count to give me the number of lines, which turned out to be a mere 4,336, showing that I wildly exaggerated in my assertion about the number of is instances. But still, there you are. There's a lot of them. And actually, if you get rid of this and just put more, then you can see the actual is instance calls all over the place in Python or in Sage. So these are many actual examples of is instance in the Sage source code. So for example, checking if names is a type string, or str actually. Checking whether gens, whatever that is a list or a tuple or a sequence, etc., etc. So this is how you do type checking in Python. And also often, in many of these cases, what's going on is there's logic which is based on the type. So in some languages, you define a whole bunch of functions called foo with different signatures. Like if foo takes an integer, then it's you have one function. If foo takes a string, you have a completely different function. In Python, you can't do that. You define one foo, and then you have to use is instance and decide what to do via a bunch of if statements. It's just different. Okay, so the video you can do sage dash. I'll write it down right here also. So sage space dash grep, and then something goes here. And then if you don't want them to all fly by, you can do type into more. All right, so I have still not written add, so let's do it. Self has attributes n and d, and right has attributes n and d. And now we just need to figure out how to add self and self and right. So, geez, we have to figure out how to add rational numbers, which let's do a little example. If you want to add these two rational numbers together, you can use the formula n times b plus a times m divided by mb. And that will work fine. If you use this formula, there's no guarantee. In fact, it's false that these will be co-prime. But it doesn't matter because our init method will divide out any common factor. I'm not trying to be super efficient or anything. I'm just trying to make something that works. So what we'll do is we'll return a new rational number. And now we just have to figure out what n and d is. For n, we could take self.n times right. That's the right-hand thing in the sum, d, plus self.d times right.n. That's the numerator. And then the denominator is the product self.d times right.d. M times b. Okay, so there we are. So we should now be able to add rational numbers. And moreover, it'll always end up in lowest terms because at this point, the init method gets called. And it will divide things out and fix things. All right, so let's try it. Let's make two rational numbers. Actually, let's make them really small. I always wondered what 2/3 and, I don't know, 3/7 add up to? Okay, so we can do print s and t and see that we have our two rational numbers, but we can also do s plus t. Wait, what happened there? Oh, I said rational, not rational number. Okay, so I have my two rational numbers, and now let's do s plus t. S plus t. It might be psychologically better if we figure this out in our head first before actually doing it, because if we just see an answer and we believe it and it's wrong, that would be kind of embarrassing. So it should be 2/3 plus 3/7, so
23 was 29.
right. Let's see if you're right. Uh-oh.
21.
Or 21, yeah, of course, because 3 times 7. So that looks good. There we are. At this point, we can give ourselves a thumbs up. We should also, hopefully instinctually, want to add this example as a test. Because, for sure, later on, you're going to take your class and be like, geez, add's kind of slow. This is not really the best way to do this. I think I'll make it faster. And what you'll do is you'll then write the code more quickly. And you'll, of course, introduce a bug, which you'll then know because you will run your tests. So let's see. Let's take this code. Oh, I don't want to act. I don't think I'll literally do this, but again, the way you would make a test is just put something like this with sage colon in front of it, and then the output as given. Okay, you know. Okay, so now we have add. What next? What should we do with our rational number? Yeah, why not? Let's multiply. That's fun. It's actually easier than adding. So, oh, I did get to show you the isInstance thing happening. So, by the way, if I do s plus some other funny thing, we should get an exception. And we do. And this should also be a test in your code. I think I will put this in the tests just because it's kind of interesting how you do that. So I'm going to modify this file to have our add method, and I'm going to put a test in that illustrates this error occurring. So if you make a, I'm just going to put these in because it's, if you look at actual Sage source code, in most cases, the examples are, and tests, take up maybe 3 or 4 times as much space as the actual code. It's extremely common, believe it or not. So that should indicate very clearly how important this is. You have to program defensively, or you're doomed. Okay, so there's that. And then let's also put in this example that illustrates doing something like this. So there's just a standard way of formatting these exceptions, and I will illustrate it. So put that. Then you put ... omitting everything in the traceback, and then you put the actual exception. Okay, so there it is. So this is a complete test, which, again, if we were to do sage-t on this file, it'll run this test. And it'll even run the check where you add to a funny thing and get a traceback and verify that the right exception is raised. Because that's really important. Like, if you're looking at the documentation for a function and it says it raises a type error, but it actually raises a value error, that's going to break, that could potentially break your code. Because in your program, you might have try colon, blah, 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 except colon type error, or sorry, except type error colon. And if a value error comes back instead of a type error, then you won't be catching it. So it's really important that your examples and so on correctly illustrate these sort of exceptions that could get raised. All right, so that's that. And it's really hard to resist running the tests. I can't resist. So it's running the tests, and they all pass. Woohoo! Okay. All right, so the next thing we want to do is multiplication. As promised, I will copy the class down here and make a new box, and we'll put multiplication here. So multiply self by right. We want a similar type check. And then this is just, I mean, it's almost the same, it's just easier. So the numerators you multiply, and the denominators you multiply. Done. And now let's take our example from before and multiply s and t. And we should get 6 over 21, which reduces to 2 over 7. Okay, great. And now we can even make expressions out of, we can do s plus t times s times t, I don't know, plus rational number, 3 minus 7. Okay, so you can have all kinds of fun. We have now made something that models the rational numbers. Of course, there are many other things you might want to do, like square a rational number, factor a rational number. It'd be nice to have a factor function that gives you its factorization of the primes. There's tons and tons of things you might want to add to rational numbers. Any ideas for other things you might want to add? What? Negation, yep. Negation, where you just switch the sign at the top. Division, there's underscore div method, underscore neg method. So neg is a unary operator, and you just do return rational number minus self numerator and then denominator. You can do pow, like for powering. So that would return the kth power of our rational number, et cetera, et cetera. And I guess somebody said div, self, comma, right. And here, it's just going to, just basically copy the mul code, but switch n and d. Or maybe switch d and n. I don't know. Let's see. Yep, that should be right, I hope. So we just added a bunch of methods, and now we can do all kinds of other things with our two rational numbers. We have to recreate them all, but now you can do s divided by t minus. No, I didn't implement a minus. I only implemented a neg, so I could go minus s over t. Okay, so now I can divide. It's easy to get carried away and implement a bunch of these and not even bother, writing little tests carefully. Don't do that, or at least definitely write the tests at some point. Actually, just for fun, let's look at the actual source code of the rational numbers in Sage, which I will track down quickly. Let's see, open user local Sage.
You were to write your tests not in Sage?
Yes.
Would you do it the same way in the
You mean in a .py in a Python file, or?
Yeah.
Yes, you just exactly the same, but in a .py file. Yep. And if this just uses the standard doc test framework, which is part of Python, and is, I guess, modeled on some similar frameworks in other languages. And in normal Python, you obviously don't use the Sage : prompt. Use 3 greater than signs, since that's the prompt in Python. Like, if you're at the Python prompt and you type, or if you're at the command line and you type Python, you get 3 greater than signs. So putting Sage : tells the doc test framework to pre-parse the input that's right here. I was just going to show you the actual rational number class. So let's see, user local Sage, current Sage 6. Actually, a funner place to look at this would be GitHub. So GitHub, one of the, probably the biggest code hosting sites these days. We have a GitHub repository for Sage where you can browse the Sage source code, the latest version. So here we are. I'm in the Sage source Sage directory, and inside of that we have a whole bunch of subdirectories corresponding to different modules of Sage. And in there we'll find one called rings, right here, because rational numbers are elements of a ring. And inside of here, there's going to be a file called rational .pyx. So the implementation of rational numbers in Sage is not in Python, but in Cython, because it has to be very fast. So it's written in a language, the name Cython, which is, so it looks like Python, but the P is replaced by a C. And I made up that name. And when I made it up, I was Googling for good names for something that was sort of related to C and Python. And when I Googled this one, all I got was a punk rocker with a big mohawk flipping you off. That was the top hit in Google. And there was almost nothing else. And so I figured there wouldn't be too much of an issue for the website to get top rankings and so on. It also sort of nicely suggests that it's something that combines C and Python. It's based, so Cython is basically a Python compiler that's based on another project called Pyrex, the author of which, Greg Ewing, was very busy and didn't have a lot of time to work on it. Pyrex is not the greatest choice of a name because it's a heavily trademarked name that's used a lot in, I guess, cooking glassware and lab equipment and so on. In any case, this is the file, which is about 3,000 lines of code. And I started it in 2005, and many, many people have done things to it over the years. Cython should look very much like Python. There's going to be a class here in a second. Yep, here it is. So it says class rational. There's some extra stuff here, and there's a cdef, which tells us that we're allowed to use extra C type annotations and so on. But if you go down in here and just start looking, there's lots of tests. There's lots of code to do nice things. So just things you might not have thought of, but over the years you start wanting to have. There's a method that gives you the LaTeX code to typeset a rational number. It's \frac. And, if you have some complicated data structure like a matrix with entries that are polynomials over the rationals, then when you ask to typeset it using LaTeX, it'll ask to typeset each of the entries, each of the polynomials that are entries, will ask to typeset each of their coefficients, and then eventually it'll get down here and call this code. So when data structures that are complicated get recursively typeset nicely, code like this gets called at the core. But there's a lot of methods here, and it just kind of goes on and on and on. And as I promised, look at the sort of code here. So here's a function that you might think, oh, that should be really easy, is perfect power, right? If I would have sat there and said, what else might you want to do with a rational number? Eventually you might have come to, I want to know whether it's a perfect power, i.e. a number like 9 or 27, a perfect power of, what does that mean exactly? It's kind of a funny thing, actually. You need to define it because everything's something to the power of 1. So it means I think it means a power where the exponent is bigger than 1. So, yeah. But it's actually a pretty subtle thing to correctly implement, believe it or not. In fact, the implementation that I think I remember doing first turned out to be wrong. It just called another library called Paris, and that was usually right. But the most naive way that you might do this is factor your number and then just check if it's perfect power. But actually, that's really, really slow compared to what can be done. You can do things that involve taking roots using floating point numbers and then checking whether when you round the thing, whether when you power back, you get the original number. And that can be dramatically faster than just trying to factor your number, which would be ridiculously slow. And so it turned out there were subtle bugs in Paris that would only happen, with input that's really big or hit some sort of subtle edge case. So some other guy, David Harvey, came along and wrote a new version, which you can see the code here, which does perfect power testing. And if you were to write C code, it would look very similar to this, except with braces instead of colons. It's nicely commented and so on. But notice, here's another example of a typical function in Sage. So square-free part is another function. It gets rid of all the squares in your rational numbers. So it's a whole bunch of documentation and then one line of code. Pretty common thing to see. Okay, again, just so you can see, I'm looking at the source code of Sage itself at the website github.com/sagemath, where we have the Git repository. And here you can actually, not only can you browse the files in the source code stage, you can browse the complete history of every file and see exactly what changed over time, how it changed, who changed it, etc. All right, so back to our story. Okay, so let's see, we have 3 minutes left. All right, I'm going to talk about decorators really quickly. So we've done enough with rationals. I'll talk about this another time. Definitely not going to talk about graphics, but since there's a homework problem that involves decorators, I better tell you something about decorators. You'll be very annoyed. So, decorators are, at their core, ridiculously simple. So, let's see. First, I'll just give you kind of a formal thing. So say you define a function, f of n and m. Let's say it returns n plus m. Okay, so it's a simple function. And let's say we want to make a, let's see, I'll make a thing called noisy, which takes as input a function. And here's what it does. It'll call the function, it'll give me back a new function that's just like the original function, except it'll print out lots of noisy information about how the function's being called. This is going to be, by the way, very useful for your homework problem. So I'm going to make a new function that takes an arbitrary collection of input, and what it does is it prints out that input. It then calls f with exactly the same input that it just got, and gets something, prints that out, and then returns it. So far I have not used Python decorators. In fact, I haven't done anything that I haven't completely explained to you before. But now look what happens. If I'm going to do this down here. If I noisy f. So if I do this, I've now defined a function f, and then I've wrapped it in a, I forgot to return g, sorry. I've now replaced f by a new function that works just like f, except it's very noisy. It prints out its inputs and its outputs. So watch, f of 3, 4. Boom, it printed out its inputs and it printed out its outputs. So you could use this in debugging or something like that. So does this make sense? I've literally used nothing that I haven't completely explained to you before. I just made a function called noisy that inside of it defines a function and returns that function. The function that's inside of there is kind of a funny function. It takes anything as input using variable number of arguments and keywords, and it calls the original function f and then returns the answer. And while it's at it, it prints out a lot of stuff. Okay? Does that make sense, more or less? Any questions about that? Now, here's the thing. The notation looks kind of funny. If I want to make a function and just make it noisy, I have to put at the very, like after I define the function, you have to do f equals noisy of f. And that just kind of looks ugly and silly. And so here's what Python decorators are. It's just a different way of writing this. If I write ampersand noisy, not ampersand, at noisy, def f of n comma m, this is completely equivalent to what I put above. It just looks way better, or so some people claim. So that is an example of a new construction in Python that I've never shown you before. It's you put this at sign and then the name of something that you can call, such as noisy, before you define a function. And what Python does is it defines the function just like it usually would, and then right after it defines the function, it sets the function equal to calling this thing with the function as input. So it just, in a sense, it just transforms this into that. And that is a Python decorator. That's it. That's all it is. Nothing more, nothing less. It's just that it puts what you're doing to the function up at the top right before the function, so it's really clear that something funny was done to this function, that it was changed in some way. And it also looks really nice. When you see this code, you're thinking, oh, at line 225, okay, the function's going to be noisy. And then you have the functions defined. Okay, I'm done. See you on Friday.